speaking to us about actions of monoidal categories in closed stabilization. As always, if at any point anyone wishes to ask a question or make a comment, please go ahead and unmute yourself at any time during the talk. You can also ask questions in the chat, and in that case, I can interrupt Akif for you. We'll also be having questions round at the end of the talk. So yeah, thank you very much, Akif. Please take it away.
I thank you for the invitation, and it's a great pleasure to talk here. So maybe before the talk, I need to mention that this is a still ongoing project, and it is joint with Özgün Ünlü. I hope he will be here, and I am sharing the link for the archive link for the talk. For the preprint, but we will change it soon because we decided to add some new things. So the title is Actions of Monoidal Categories and Stabilization. So let me start with motivation. The motivation comes from stable homotopy theory of spaces, and the classical stable homotopy theory itself, and the classical stable homotopy theory of topological spaces studies objects called spectra. And in the first talk of this year, Nick Gursky mentioned about them, and he talked a lot about them. I think he talked give some information about them. So let me at least give the definition for now. So a spectrum is a sequence of pointed spaces together with a sequence of homotopy equivalences like this. So actually this is omega spectrum, and they are important because they can represent generalized cohomology theories. So for every spectra there is a cohomology theory, and for every cohomology theory there is a spectra. And the general idea started around early 19th century by Freud-Antle suspension theorem, and and then continue with Spanner. By using motivation, they Spanner and Whitehead construct a category called Spanner-Whitehead category, and then spectra, the idea of spectra came out, and all of these things invented before category theory itself. So later, spectra can be defined as stabilization of homotopy category of spaces, or the ordinary homotopy category. So the thing is, the idea is the loop space functor, which is given by so this is the pointed S1, and top star is the pointed category of topological spaces. So everything is pointed for this talk, by the way. I mean, if I mentioned them, you understand that it's pointed. So the loop functor is not invertible on homotopy category. So to formally invert, you take this limit of this diagram, inverse limit, and then the resulting category gives you spectra. And it can be generalized to any pointed homotopy theory. Homotopy theory, you can understand like you can. I mean, it can be either a relative category, or you can also think that as infinity one category. But so I mean, by I just say homotopy theory instead. So if you have a for every homotopy theory there is a loop functor. If it has homotopy fullbacks, so if this is X, then loop functor can be taken like this. And if you construct this diagram, take the limits. I mean, limits. If you are dealing with infinity one categories, then it is one limit. Then the resulting limit on this resulting limit, the omega, the loop functor, becomes invertible. But okay, this picture is nice, but sometimes there are multiple loop functors. For example, in equivariant homotopy theory, if you talk about the category of G spaces and G maps, then for any G representation, you can have a loop functor like this, where SV is the pointed. So SV is the one-point compactification of the disk. So the point is SV here. And if you try to invert all these loop functors, you get something called genuine G spectra, which is indexed by G representations. So, but this does not fit into this picture. For example, you cannot, if you take the loop functor, then you don't get this category. And this category has objects as pairs where for every representation there is a pointed G space EV, and for every other representation W there is G homotopy covariances. And by a similar reason, G equivalent homotopy cohomology theories are naturally graded over ROG. Here, this ROG is actually not the representation ring. This is, this is, I mean, actually, this is just one-point compactification, but you can just take, it's the compound dragon construction. ROG is a monoidal category. I mean, this is given in, magnify a little bit, in Peter May's book. It is defined as the monoidal category of G representations with G equivalent isometric isomorphisms as morphisms. So this is it appears in classical book, and his actually one of other motivations of this work is his definition of ROG graded cohomology theories just looks very much like an action of this ROG on the collection of cohomology functors. And also there are the suspensions, so there is an okay with the suspensions, and they satisfy certain axioms. And by the way, obtaining these axioms take quite long in the history of equivalent homotopy theory, and they found the correct axioms given in this book. So the goal of this work is we want to develop a unified treatment to spectra, so that with exotic indexing, I mean, sometimes, for example, there are spectra indexed by, so they are indexed by pairs of integers or pairs of natural numbers, and there are, for example, cohomology theories with exotic characters. For example, there are phi-graded cohomology theories or ROG-graded cohomology theories, etc. And we will do it by considering actions of monoidal categories on homotopy theories or on categories. We can themselves. And we will investigate further consequences of this approach. And what is action? I will, by action, what we mean is by action. An action is a two-sided action, but mostly we work with one-sided actions. But still, what we want to do is, here with I is a symmetric monoidal category, M is any strict 2 category, and Bi is, so when such an I is given, there is a 2 category with single object, and Bi op is it's one cell dual. We just invert one cells. So actually, I mean, it's like changing A tensor B to be defining a new B tensor A. So in this one gives the monoidal category where the tensor is inverted. And normally we didn't assume symmetry in our paper, but for this talk, I mean, for convenience, I assume I is also symmetric monoidal. And we also don't need to assume strict. For example, ROG itself was not strict, but there was I mean, you can either consider, I mean, if your category is not strict, then you can take strictification. and look at the strict functors. This is the same as the looking at the ordinary monoidal category and non-strict, I mean strong functors or slow functors. Okay, so an action is a two functor from this. So bi times bi up to such that the single object is sent to A, and every pair gives a map. So if you have, for example, if you have a pair of objects in U and V, so I mean there are morphisms in Bi and Bi up, then alpha gives a map from A to A. And and the idea, what we want to do is we want to define a kind of equivalence for such actions, such that acting from the left and from the right at the same time will become like acting. Okay. I mean, so that's if you act an object in A from the left and from the right, the same thing, then this will be an isomorphic to this will be isomorphic to U itself. So action from the right will cancel with action from the left. And why are we doing this? Because if this was a group, then if acting by inverses, for example, if everything was invertible in Vi with respect to tensor product, acting with inverses was a right action. And if you act by A, then G from the right, this action can be defined by acting from the left by the inverse, which is the right action, and they cancel each other, and you get identity. So this is why we consider two-sided actions. But we will introduce an exotic, I mean, a new notion of equivalence for such actions. Okay, so let me give for some examples first. For example, if M is category of all categories, you can think as small categories, but we can also consider Grothendieck universes, and I mean, you can take small in some universe. Then category I acts on I by translation from the left or from the right. That means if, for example, translation from the left, mu L sends Ij to I, so the single point to I, and this is, I mean, J will not have an effect. It will be mute on the right side. So this Ij will send the map I tensor something from I to I, which sends any K to I tensor K. And morphisms will be sent to related natural transformations. And if, for example, if you have one morphism in M, then there is an associated actions of natural numbers. So actually, I mean, we are like considering the dynamics of such maps, such functors. So the N action, if we don't consider any natural transformation between them, this will okay. This is a monoidal category with addition with trivial morphisms. Can be given as if you want to take the left action, it is alpha, and M will be just the composition of alpha with itself. And if you have a morphism, then it will be an action of a monoidal category with objects as M, but morphisms are generated by, for example, the morphism, a morphism F1 to 1, so freely generated by this thing. If we have multiple morphisms, then we can think this system as a action of a free monoid, where such a word will be, and T is mute here. Again, we can just look at one-sided actions for now. So such a word will be sent to the composition. And the powers means you are composing alpha by with itself and times. And if there are two morphisms, then it will be a action. Okay, it will be an action of a monoidal category. Actually, you can also think that as a subcategory of the endomorphism category. So this is a monoidal category and submonoidal category of the endomorphism category generated by these maps as well. I mean, it depends your choice. I mean, what your taste, what you want. Okay. So I said in the abstract that we will give the stabilization in terms of two ends. So the two categorical end. And if cat is the two category of categories, and F is so C is any small two category, and F is a two functor, then the end is defined by this equivalence. So we are looking actually weak to end. This means, so this is not isomorphism, but an equivalence. Of course, we can change it. So we take the pseudo functor category, but I mean, if you can make it strict, or you can take lax functors. If you take lax functors, for example, when we do stabilization, the resulting stabilization will look like the press spectra, where the maps are just where the structure maps are just functions, or actually morphisms. But we like them to be isomorphism. So for this talk, we take pseudo functors. And so this definition of end is okay. Maybe I should magnify it a little bit. This we take the definition from the paper by Bird, Kelly, Power, and Street. Flexible limits for two categories. So we just take the home weighted limit in their definition of weighted two limit. They call it bilimits in that paper. So as I said, we will define equivariants. So what are the equivariant morphisms? First, if we have alpha and beta, these are actions on objects in M, A, and B, respectively. Then there is an action on the functor category of functors from A to B, which can be given by this composition. You take xy, this is sent to yx, xy. Here, so this is, and from here you take a functor alpha of times b, and you get the home functor here in M, and the resulting composition will define an action on the category of functors. So M is a two category, so this is so it's enriched in cat. So this is a category, and we denote this action by alpha beta, and the category of I and covariant one morphisms from A to B is given by this end. We define it by this. Let me first talk about how end look like, and how then for example, in the case when M is equal to cat, how equivariant morphisms look like. So if M is cat, then this is equal to the category whose objects are pairs A sigma, where A is an object in A, and sigma is a natural isomorphism from the right action on A to left action on A. So from A dot U, so U is an object in I here. I should also write that. I. And it is a natural isomorphism from a U to UI. And also, this satisfies some coherence conditions. So basically, this diagram commutes, this triangle commutes, and also the unit in I is sent to. Oh, okay, this is the identity on the alpha 1 1. So which is just actually isomorphic to A. So identity on some object isomorphic. And morphisms are maps from A to A prime that commute with the structure maps. Later, I mean, you will see this map will look like the structure maps of spectra. And what are equivalent one morphisms? Equivalent one morphism, if in this case, if M is equal to cat, and I equivalent one morphism from A to B is a pair F sigma, where F is a one morphism from A to B, and sigma is an natural isomorphism. And it satisfies coherent conditions like this, but it is a little bit more complicated, so I write it. So basically, the equivalent morphism. So this is different than the equivalent. So between biactions, it is f u dot. So f u dot a. So u is in I again. F u dot a. If and f, ux by right on this is isomorphic to u dot ux from the left of f of a dot. So this is true for every u in U actually. And this satisfies other conditions. And again, one morphisms are so compositions of one. Okay, compositions of unfortunately composition of I equivalent one morphisms are not defined if we have actions on both sides. But if they are mute on one side, for example, if both are one-sided actions, then compositions are well defined. They are a little bit complicated, but let me show it here. Where is it? Yeah, compositions are defined like this. And associativity can be seen. But I mean, if we, as I said, we find a new way of writing it, composition will correspond to some sort of day convolution in this new way. So we define a category IM of I objects and I equivalent morphisms in M. Actually, this is a two category with coherent natural transformations. So objects are objects of M equal with an one-sided A action. So one side is mute, that means they don't have any effect. Morphisms are I equivalent one morphisms and with natural transformations between them. And this is not very convenient category because, for example, it doesn't have products in general. If you multiply, okay, if you take the product of a left action with a right action, the resultant object will not be in M, but it contains both of these categories, which are convenient enough to work with. So we actually define stabilization from, as a functor from here to IM, and we return to here. I mean, it can restrict on these categories. So what are stable I objects? I mean, there are, of course, if there is a homotopical structure on A, you can just, okay, if alpha is an I action on A, then we say A is stable with respect to this alpha if this is a one equivalence. And for example, if we are working with homotopy theories, then we can say that it is a weak one equivalence, which means it's an equivalence on homotopy category. So stable, the full subcategory category of stable objects will be denoted like this, and there is an inclusion functor. If exists, the right adjoint of this functor will be called stabilization, and the left adjoint will be called co-stabilization. But I mean, maybe we can say it right stabilization of left or left stabilization better. I don't know. Anyway, so stop will be a function from here to here if exists. And we give a construction of this for this talk. I will just give a construction for cat. But also, I mean, a similar construction for works for rel cat relative categories. So if we have a I action alpha on A, that is mutant, right? So this is the left action. This is left I action, and mu are the I action on A given by tensoring from the right. So this is the right action. So, and if M is a category with cat powers, so there is a powering over cat, then there is an I action induced on this power object, where I is now considered as an ordinary category with the left action. Let me also mark them. This is mu r, this is alpha. And we define and we give a construction, something called inv. Inv of alpha is defined as the end over this action, end of this action. So this this powering of mu r alpha is the I action induced on the powering. So it's just similar to the functor like this. Where is it? Huh. But this time here we change it with powering. So compose like this, and then take the mu r here, and then cat here, and put the powering here. We get a action. It is this action. Okay. So in the case when okay, maybe left translation on I induces an I action, a right I action on this inv construction, and there is an evaluation functor which is induced from 1 to I. And what does this look like from the earlier construction of and if M is equal to cat, then the inv here has objects as pairs f, where f is a functor from I to A, and sigma is a okay, well, let me write sigma in detail. Sigma is a natural transformation from look back. From f of A to f of say u to so alpha. So for each v, there is sigma v from fu to alpha v f u tensor v. So if you okay, if you look at the actions here, let's return equivariant maps. Here, action on. So this is if this is I, if this is A, this has a right action and mute on the left. So this will be just A, and this is mute on the right. So this will does not have an effect. So there will be just FA here and an isomorphism. And here we have action of U times F and action of A tensor U. Here A was in, maybe I just say, instead of A, just say B. B is in the monoidal category I. So that is why we get a map like this. You see, it very much looks like the structure maps of spectra. And the evaluation just sends F to F of 1. So where 1 is the monoidal unit in I. So it is the evaluation at F. First I used sigma instead of F, then let me change it. And the action on this inf is given by, in this case, call it alpha bar. Alpha bar is a right action. So I don't write the left part, I just put 1 here. So it sends F to the map, which sends V to F of U tensor V. So this is the right action. And this action is, in fact, if I symmetric monoidal, this is an invertible action. So let me give some, an important theorem about stability. A is stable if and only if this is a epsilon A is a 1 equivalence. This map is a 1 equivalence. And if we are working with homotopy theories, then we can also add weak 1 equivalence here. So a weak 1 equivalence means it's 1 equivalence in various categories. And also, if we are working with infinite 1 categories, then we can say it's infinite 1 equivalence. And this in L defines a functor from IM to. So this construction is functorial and defines a functor from IM to IM stable, such that this thing together with epsilon is a stabilization with respect to alpha. It satisfies desired universal property. And how do you see this? Let me give a brief sketch of proof. So if M is cat, this proof I will just give it for M is equal to category of categories. So if F sigma is in L, then where F is equivariant functor from I to A, sigma is an isomorphism like this, then you see if you so by definition, this was just alpha bar of 1 U of FB. So the composition of alpha with alpha bar, so the left action with right action, will give you just F. So this is FB is so this gives something isomorphic to F. So the alpha bar, the action alpha bar is an inverse for alpha. So the alpha bar is an equivalence. So alpha restrict. So an action induced by alpha gives an inverse of the equivalence. And this is so L is stable with respect to alpha bar, and universal property follows from the fact that this epsilon star is full and faithful, and it's in fact an equivalence. So the epsilon star is the functor induced by epsilon. Where is it? Epsilon A. So this epsilon, and for whenever B is stable, then there is an inverse here, which sends F to B to L, because whenever B is stable, epsilon B has a weak inverse, and we compose with this inverse with the induced map F star, gives us a functor from E to M. I mean, it is. We also need to mention the sigmas so that they are equivariant, but they can be also given in terms of sigma of this F. So this is an equivalence of categories. So it means it's also so equivalence. So it's full and faithful. Thus, L is a stabilization. Okay, maybe I can continue with some examples. Oh, sorry, some consequences. So there is a problem addressed in Lurie's higher algebra book. Stabilization from homotopy theories to stable homotopy theories is not a functor. So there is no stabilization functor. And one of the reasons is because of lack of equivariance. It is like you take some things with actions and you send them to things with invertible actions. So and in the book, Lurie mentions that people work with. People try to tackle this problem via goodwill calculus. And if we add equivariance in the picture, then we get a functor. I mean, if we consider, for example, I equivariant homotopy theories and I stable homotopy theories with equivariant maps, then there is a stabilization functor. And also in this setting, so we can you see, I mean, we can put different indexing of spectra and different indexing in cohomology theories in same picture. Actually, cohomology theories also become stabilization of cohomology functors with respect to suspension actions, for example, because there are the suspension maps, and the suspension maps will be obtained as the sigmas. So from these sigmas here, these things. And another consequence is it establishes a duality. I mean, up to now, I only talked about the right adjoint. There is also the left adjoint. In some cases, it can be constructed. And if, for example, if M is equal to category of categories, or it is a category of relative categories, then, and if we are only the right actions, then this can be give some sort of stable category, stable homotopy theory via categories look like the Spanner-Whitehead categories. I mean, there are constructions of stabilizations like objects are pair of objects A and morphisms are maps from in the stable range. So such constructions can be obtained. Such constructions correspond to. Sorry, this is wrong. Correspond to co-stabilization, the right adjoint, the left adjoint of the inclusion. This is right adjoint to inclusion of stable, and this is left adjoint to maybe better. The previous one was wrong. And this can be constructed, for example, in terms of Grothendieck construction. Maybe after giving some examples, I will also, if we have time, I can also talk about them. So, for example, let's obtain ordinary stabilization as from this setting. So take the monoidal category I as natural numbers with trivial morphisms and with addition. A as a homotopy category of topological spaces, and we have the loop functor here. And look at in L, this has objects as E sigma, where E is a functor from N to top, and sigma M is a sorry, by the way, this sigma M is an isomorphism, actually a homotopy equivalence from En to omega n En plus 1. Actually, this we here don't take the whole, but we just do okay, we just take stabilization in relative categories. This construction, okay, can be obtained as a whole homotopy limit, and it is, I think, it coincides with the homotopy limit construction in Julia Bergner's homotopy limit of model categories paper. And coherence conditions are automatic here. And so this actually just looks like the category of spectra. I mean, just change this into something like this. It is just the category that's mentioned in the beginning. So the morphisms are the maps commuting with sigma m, so commuting squares. And if I set I to be the ROG, the monoidal category of G representations and G isometric isomorphisms, actually, I mean, this is a 2-1 category. The B of this is a 2-1 category because everything is an isomorphism. And take direct sum as the monoidal product, then take A to be the G topological spaces, and do the same construction. We get so take the action as the left action given by I mean loop space, taking looping with SV anekoyan, and then in L has objects as pairs E sigma, where E is a functor from ROG to G top, and sigma is a natural isomorphism. Or sorry, if we think this as a relative category, this is a weak equivalence, and take the take it as homotopy limit. This is a weak equivalence. So this just looks like the spectra index by representations, and also this satisfies certain conditions. If you let me return there. So okay, from these diagrams and this identity, the coherence conditions for spectra follows. I mean, which are given in Peter May's book. So what are they? Okay, E sigma satisfies. So this diagram commutes for any F U to B, and this triangle commutes. So where this map is composition here, and these are okay. This is the same as G equivalent spectra given in this book. So this a lot of authors, but I think so. Equivalent homotopy and cohomology theory, and it is mostly chapters between 9 to 13. And you can, okay, this, I think these chapters belong to Kostanobel, Piacenza, and there is also a new construction which I want to give. Consider the category of X spaces. So this is, if B is a space, top B is a category whose objects are maps from X to B that admits a section. So morphisms are commuting triangles. So, and this is a pointed category where the point is the identity map on B. And homotopy theory of this thing is called parameterized homotopy theory. I think it is also you can. There is a book on parameterized homotopy theory, by Sigurdsson, but in this book the spectra is given by n-graded spectra, usual spectra, and you can extend the grading to vector bundles over B. Here, I is vect B, the monoidal category of vector bundles over B. With again, you can take only fiber-wise isometric isomorphism if you like, and for every vector bundle, construct a sphere bundle by taking fiber-wise this bundle divided by sphere bundle. So fiber-wise 1-point compactification. I mean, you don't just take the Tom space, but you obtain a sphere bundle. And this has a zero section. So it is a so this thing with so can you can okay, there is a map from Xi to B. It has zero section, so it is it's an object in this category top B, top sub B, and you can define an action, so a left action again, call it omega Xi, as a home space from S Xi. So omega star of some, for example, F is home B S Xi. Actually, this map, let's say. Let's call it sigma prime, Xi prime to F. So, I mean, as a home object in this category. And this defines an action on B. And by the way, I mean, in May's book, it's also mentioned that this is the Cartesian closed category. Sorry, this is Cartesian closed. So stabilization with respect to omega gives a category whose objects are parameterized spectra indexed by vector bundles over B. And maybe before we finish, let me talk a little bit about general framework of this thing. So if we have a map, then we have an N action. And if we have several maps, then we have an FS action, as I mentioned. And this map is invertible, means the action is reversible. So if you categorize this whole idea, you get the notion similar to stabilization. So action is reversible means functor is invertible. And as I said, I think we have time, right? Okay. So if you, for example, take alpha like this, a right action on A. So this is a relative category with weak equivalences A. Then the right adjoint will be a construction like this, which can be given in terms of Grothendieck construction. So this is actually a homotopy right adjoint, and this I think, I mean, this corresponds. This is proved in a preliminary version of a paper by Lennart Ayer. So it's unpublished, but it is available in his webpage. You can look it up. So the homotopy columns in the relative categories can be given as Grothendieck constructions in terms of Grothendieck constructions. And if I look this Grothendieck constructions, then so BI has one object, so the objects will be pairs here. And let me also describe what this is. This mu r. So this cotensor, just take cotensor just is the product I times A. Sorry, this is tensor, not cotensor. Mu r times mu r dot a is an action on this product, where on the right we have I x from the right, and on a also I x from the right. So composite from with inclusion, and take the Grothendieck construction, and the resulting Grothendieck construction has objects as pairs u in I, a in a, and morphisms are triples v, p, f, where v is any object in I, so it is actually one morphism here, and pf is a pair of maps from U tensor v to a dot v from u prime to a prime. And here, if, for example, in the case where I is equal to n, a is equal to finite CW complexes, and alpha is the suspension of finite CW complexes, then this construction, so this construction's homotopy category will be same as the spinor Whitehead category. And this is actually, I mean, this general construction of co-stabilization is actually different from the one of stabilization. So let me also mention lastly that they are different. For example, in the case of that MB just sets in a trivial way so it can be considered as a trivial, as a category in a trivial way. And let's look at this n action. So here we have a discrete set. So let's describe the action as in automata style. So this means, so if n is generated by 1, so 1 acts like this. So it sends, let's say, A1, so A1, B1, A0, A0, let's say C, C1, C2, etc. So this means 1 sends these elements to, so A1 to A0, A0 to C, B0 to C, etc. And if you take stabilization of this, if you apply stabilization just in a very strict sense, you get 2 components like this with action of 1 given as this. So this is action of 1. But if you take co-stabilization, you just get 1 line. Because I mean this stabilization, for example, in finite case, it takes the maximal subspace. So sorry, maximal subset on which action is irreversible, and co-stabilization takes maximum quotient in which action is reversible. So here, this stabilization identifies, in this case, the reversible parts, each of the parts. If you restrict on this part, which is maximal in some sense, and action is reversible here, you can trace back where it comes from. And if you take the quotient, then these 2 things identified, and you get one. They are different. So maybe this, and if you, so thank you for listening.
Thank you very much, Akif, for the great talk.
I thank you.
Are there any questions or comments for Akif?
I might just ask a sort of a general question. is it necessary to have the same monoidal category acting on the left and the right? Because if you allowed them to be different, then you would get a nice bi-category of bi-actions. Okay. I don't know if you can use that, or if it's necessary to have the actions by the same. Yes.
Actually, I mean, it's actually not necessary. I mean, I mean, you can do all of these without defining that, but it makes the proof very convenient. I mean, these proofs become easier, and these diagrams here, for example, can be obtained in a much easier way. So these are like, but I mean, it's not really necessary because we are restricted on one side. But two-sided actions, I mean, I take two-sided because it's like right action canceling the left action. So I want to define a notion of equivariance between left action and right action.
Okay.
Because in monoids, you cannot carry the left action to the right. Unlike groups, in groups you can do it. So for the same reason, in monoidal categories, you cannot carry the left action to the right action. So you cannot define an equivalence relation between the two processes modeled by action from the right and action from the left.
Okay. Yeah.
But for stabilization, I mean, to construct stabilization, we can just use left action on all the way, and then we still get something else. But I mean, the proofs may be a little bit more difficult. I mean, I didn't know the proofs without using one-sided actions. Sorry, without using two-sided actions.
Okay.
Yeah, thank you.
Thank you very much, Bob, for the question. Maybe Carlos can ask this question.
Hi, Mehmet. Well, my question, I'm a topology algebraic guy, so it's, well, suppose that I have, or you have your favorite commodity theory, like boarding,
Homology?
Yeah, your favorite commodity theory. So this stabilization process or co-stabilization process or this action by monoidal categories, what will imply concretely? For example, what I can do with that?
I mean, you mean the construction?
Yeah.
What does it imply in homology theories?
Yeah, for example.
So you can obtain the axioms of, for example, homology theories with exotic gradings from category theoretical framework. I mean, it just normally this axiom does not follow from anywhere. It's just like, okay, this must be coherent, etc. People just decide that. But here in this construction, the axioms follow because we have, I mean, because this is this is the properties of two categorical N. Actually, I mean, they follow. They can also follow from. You can write the homotopy N in the case of relative categories as a cobar construction, and then, I mean, as a sort of cobar construction, and then take the two truncation. And in, maybe I should also mention how it works on cohomology theories. So you have a category A and take a right action suspension action here on A, and this abelian categories take the trivial action on this. Look at the functor category, take the cohomology functors from A to AB, and this has an action induced by the right action. This has a left action, so induced by the action on the first coordinate. So left action, let's call it sigma again. And if you stabilize by, if you take the stabilization of this thing, so that means if you take the inv of this thing, then what you get is a cohomology theory. What you get is, I mean, anything in the stabilization will be a cohomology theory. So it satisfies, for example, if I is, so if I is equal to ROG, then it gives the axioms for ROG graded cohomology theories. From, I mean, you deduce the axioms of cohomology theories from the construction of 2N. By the way, the construction of 2N, then these diagrams they appear in also they appear also in This is the Cohen book by Oscar Lorenzi. So maybe I should.
But assume, for example, supposing cohomology theory, this stabilization are they show, for example, in the standard operations. This
I see.
Yeah,
Okay.
that this structure really show in some really structure in cohomology theory, or for example, in borders. Yeah.
Yeah, but I believe so, because but we haven't studied that. But the morphisms of you see, I mean, here the morphisms in I induce functors, sorry, natural transformations between homology theories, which means, I mean, and by definition, the natural transformation between homology theories is a, or cohomology theories, sorry, is a cohomology operation. So standard operation can be okay. Normally, take for example, not n but action of all spheres, and maps between sphere, a map between spheres will induce a cohomology theory. Sorry, a operation, a cohomology operation between cohomology theories. Or you can, for example, obtain Stirnov squares, or or the odd order. Sorry.
The co-stabilization are not cohomology operation, no? Are another things.
I mean, if you have a map f I to j, for example, in I, then so what is the what common? Okay, what are the objects of this? This is object of this is a functor h from I to cohomology functors, abelian category, where it's sent to hi, let's note it like this, together with the suspensions. And if there is a map from I to j, then this will induce a map from this will induce a natural transformation from hi to hj, or sorry, other way around. Forget, sorry. Should be hop.
Okay, then yeah. So I see. Yeah. Thank you, Mehmet.
So I mean, but I mean, it depends on which morphisms you add in I, which ones you consider. I mean, you can do it without using any morphisms. We so far didn't look the actions of morphisms a lot, but actions of morphisms also become relevant when you want to consider cohomology operations.
Okay, there the monoidal category is just the integers.
Natural numbers.
Natural
addition. But if you, for example, add one morphism between two natural numbers freely, then it will give a natural transformation between cohomology functors. And I think natural transformations between cohomology functors are cohomology operations. They call it.
Okay. No. Yeah. Thank you. Now I understand.
Thank you very much for the question, Carlos. Are there any other questions or comments for Akif? Okay, if not, let's thank Akif again for the great presentation.
Thank you.
Thank you. It was great having you here, Akif, finally.
So,
Well, we always
in-
have you in